And hello everybody, welcome to the stream. We're going live, right? Give it a second. Yes, we're live. Alright. Hi everybody, welcome to the stream, and today we are going to be continuing through Practical Common Lisp. You can follow along at gigamonkeys.com/book. And, yeah. So last time got interrupted, and it was also going pretty slow, so today we're going to try and go a bit faster. You may or may not notice that my setup is different than before. I'm on macOS now. Don't worry about it. I've got Slime all set up in Emacs over here, and it's no big deal. Very similar setup to last time, so let me know if you can't see something. I mean, other than this text, which is very... Actually, like, zooming in actually works on macOS because of the trackpad, so it might not be as big a deal. But yeah, if you can't hear the music, or if my voice is too loud, or the text is too small, let me know in the chat, please. I'm still pretty new at this, so... Let's go. So, last time, if you missed it, we went over just kind of the basic type system of Lisp, of Common Lisp specifically. This is Chapter 4, Syntax and Semantics, and well, if you know anything about Lisp, you've seen the parentheses. You know how types work, how like numbers and strings work in other programming languages. It's very, very similar to that. True and false values are t and nil, and that's exactly the same as with an Emacs. There's some stuff about how the compiler works, which is that it's basically the reading and evaluation are two separate processes, but that's not really a big deal. Lisp is made up of S expressions, which is either a unit of a type, or it's a list of atoms, which is just anything else that's not a list. And the entire syntax is just made up of S expressions. There's also function calls, which are also just S expressions. That's how they're written, and that's how they're evaluated. So like, when I do +1, 2 over here in the REPL, what I'm actually doing is I'm plussing 1 and 2. I'm taking 1 and I'm 2. It's the list. It reads the list of plus and 1 and 2, and says, okay, plus is a function, and 1 and 2 are its arguments, and so it pluses 1 and 2 together to get 3. And that's what's actually going on there. It's very simple. The end of the function block is the end of the list, that the first element of which is the function. So it's like other programming languages, except a little bit more consistent. And of course, arguments of functions can also be lists, and they will also get evaluated as the order of operations goes, with parentheses. And that's very nice. However, there are also these things called special operators, which do not necessarily evaluate all of their arguments. Those are also called special forms in other dialects, such as eLisp. If is one example. So if we give... I'm getting into the weeds here. But basically, if actually evaluated all of its... my keyboard input is slightly broken over here, don't worry about it. Basically, if this if form evaluated both of its, or all three of its arguments, I guess, it would format both of them, but it only does the one. It does not even evaluate this this no expression, because if is just special like that. And the way it's special, there are only 25 that are like that, but even fewer are actually like super relevant. Keyboard typing sounds like popping on the microphone. Is there a way to fix it? You mean that? Probably. Let me see, because this computer is, actually maybe not, that might just be the way it sounds. So, because, I am not using, DroidCam, it's not showing up on this version of OBS for some reason. And I thought that I installed it, but it seems not to have worked. How about this? I'll just try not to type very much. How's that? Wait, does it really sound that bad? DroidCam. Okay, I can't tell. Let me type a bit. All right, how's that sound? And I thought that I installed it, but it seems not to have worked. How about this? I'll just try not to type very much. How's that? Wait, does it really sound that bad? DroidCam. Okay, I can't tell. Let me type a bit. All right, how's that sound? And I thought that I installed it, but it seems not to have worked. Okay. Yeah, I guess we're just gonna have to deal with that. It's not bad enough to restart to fix or anything, because the microphone is just built into the computer. It's an M1 MacBook. It has no moving parts, except for the lid, obviously. There's no fans or anything. It's like completely solid state, because of like efficiency, I guess. So yeah, special forms or special operators, which are like functions, but they don't evaluate their arguments. We looked at if. There's also quote, which just returns whatever you give to it without that. Oh, well, I didn't use Mac before. That's why. It's yeah. I've been jumping around. Last stream, I was on my ThinkPad, but unfortunately, it seems to have forgotten how to charge, and so I ran out of battery trying to fix it, and I don't have any way to charge the battery besides to use the charging ports, which are broken because there's a bug in the BIOS or something, and maybe you could update the BIOS if you had power, but I don't have power, so it's bricked right now, so I can't use that one anymore. And that one was running Windows, because I was doing like a challenge, but oh well, whatever, doesn't matter. Anyway, quote, when I get back, I'm away from home right now. If I get back home, I've got my whole Linux set up that actually works pretty well and is nice, and I love it. But it's a little bit slow, it kind of chugs when streaming. So there's gotta be a workaround for that. I don't know, it's all a big mess, but it mostly works out, so who cares? Quote is special like if, in that it does not evaluate its argument, it just returns it. Which, of course, the quotation mark is also a shorthand for the quote function. When the reader sees this single quote symbol, it reads that as the quote function, which is a pretty cool little trick, and this is also how it works in Emacs Lisp. So if you're familiar with that, that's the same thing. Yeah, from the evaluator, both of these two forms look exactly the same. It's just a matter of it's being transformed by the reader before it gets to the evaluator part of the actual Lisp environment. In general, the special operators implement features of the language that require some special processing by the evaluator. For instance, several special operators manipulate the environment in which other forms will be evaluated. One of those is let, which creates variable bindings that only apply within the block. So for example, my x as a variable here is undefined, but if we do let x be 10, and then I evaluate x, boom, x is 10, but that only applies within that let block because x outside of it is still undefined. Alright, so that's functions and special operators or special forms. There is also, though, macros. While special operators extend the syntax of Common Lisp beyond what can be expressed with just function calls, the set of special operators is fixed by the language standard. Macros, on the other hand, give users of the language a way to extend its syntax, which is a fancy way of saying that you can define your own operators. Similar to how if works, you could define a macro that only evaluates 1 or even 0 of its arguments without having to be, without them getting passed through to the evaluator. It would merely read them and spit them back out, or act on them in ways other than that. Now, macros are one of the trickiest and weirdest parts of Lisp, but also one of the coolest. There is this other book, let me pull it up real quick, let over lambda .com, I believe. And let over lambda is basically, it is a book similar to this, but about Lisp macros and how they actually work and how to use them even more practically. The examples in Practical Common Lisp here, like we looked at a couple streams ago, are a little bit contrived, but let over lambda's examples are way less contrived. But like as a trade-off, though, the material is harder to understand. I recommend reading it over. I recommend reading it and then going back after 4 or 5 months and then looking at it again, and you'll understand a lot more. It's one of those things. It's like a personal benchmark. So the way that macros function is they take arguments and they do not expand. They don't actually evaluate them, but they do return what's called an expansion of their arguments based on the actual definition of the macro, which is similar to how you define a function we saw earlier. And then that expansion can be evaluated in turn. It's important to keep the two phases of evaluating a macro form clear in your mind. It's easy to lose track when you're typing expressions at the REPL because the two phases happen one after the other, and the value of the second phase is immediately returned. That's what was a little bit confusing before in the first stream, because we were doing macros and I was surprised. I thought the macro would return a list that you would have to evaluate, but no, it just does it. It just does it right away. So when you actually go and compile a file, the macros get expanded out at compile time, but then into their expansions, which then get evaluated at runtime, which is kind of different. Because macros generate their expansion at compile time, they do relatively large amounts of work generating their expansion without having to pay for it when the file is loaded or the functions defined in the file are called. So the other effect of this is that the arguments you pass to a macro do not have to be these S expressions or quoted forms or anything particular. You can parse them kind of however you want within the definition of the macro, and it'll just do it. For example, we looked at backwards earlier, which you can give it a list that would not be valid, but it will turn it around so that it is valid. And they're going to talk more about macros throughout this book. The important thing to realize right now is that they're different from functions, and they cut a little bit deeper than functions do with regards to evaluation and understanding of the code itself. All right. Pardon me, cheese balls. Okay. Truth, falsehood, and equality. So we've heard of true or false. Now get ready for T or nil. T just means true, and nil means false. Everything that is not nil is true. So one way we can test that is I think not will work. So not true is true, but and not nil is nil. But if we look at just like a number or something, you can see that numbers are true, and it's going to turn out that symbols are also true, as well as, of course, strings being true. So everything that's not nil is true. The one cool and surprising thing about this, at least in the beginning, is an empty list, just open and close parentheses with nothing inside them, is nil, and that is actually how nil is defined. Nil is emptiness. It is the lack of what do you call it? Okay, there we go. Nil is the lack of elements in a list, and of course you can quote that null list, and it will also be nil. And we use nil here as just like a variable that is always defined as nil, but you can also, of course, quote nil, and that will also return nil. And that's just what this says over here. And that also works with true, so, just a plain t variable just means true, but also quoted true is still true. Using phrases such as the same thing, of course, begs the question of what it means for two values to be the same. As we'll see in future chapters, Common Lisp provides a number of type-specific equality predicates. There's equal for numbers, so like equal 5, and you could say like, 10 over 2, and that's true. There's char equal for comparing characters, and so on. And this is the part that gets kind of confusing, and I've never really quite understood. So there is also EQ. So what happened? Are true and true equal? Apparently they are. So EQ tests for object identity, whether objects are identical. However, some objects that look the same and even happen to be the same may not actually be identical. There's issues with numbers. Basically, the language standard doesn't actually define whether EQ 3 and 3 will return true or false. Here, as you can see within SBCL, it's returning true, but it certainly could return false, and that is a problem. So we shouldn't use EQ to compare numbers or characters, which, well, I think it mentioned earlier on that characters are just numbers. I don't know if I ever mentioned that, but like, oh, that's not how characters work in Common Lisp. I don't remember how characters work in Common Lisp. I don't care. We're not moving on. That's what. Okay. Welcome to the stream. If you're just joining us, by the way, we are just very briefly going over the type system of Common Lisp as well as its equality operators. EQ is fine. It can just compares if two objects are the same, but numbers aren't always the same, even if they are the same number. So, yeah. There's also EQL, which is exactly the same, except it does work on numbers, so EQL 3 and 3 will return true. But for example, if we want to do something funky with floating points, it'll return nil because 3.0 has a floating point value is actually different from 3, and that just has to do with how floating point operations work, which there are much better videos than mine, so I'm not going to explain it. There are much better videos on, I don't know why I said than mine, because I don't have a video on floating point. Particularly Jan Measley, a fellow Mitch, has a great video on floating point. How floating point works. He's the Hangman guy, you might have seen. Did the Hangman video. Blew up a few years ago. So, yeah, that's, there's two schools of thought about when to use EQ versus EQL. And some people say that you should be using EQ whenever you can. Just don't compare numbers with it, and it's fine. The other way of thinking about it is to just always use EQL because it actually works. And it's easier to remember to just write. And this book that we're following is just going to always use EQL, so I think I will too, because, yeah, dynamic typing is stupid. No comment. For now. The other two equality products, equal and equal p, are general in the sense that they can operate on all types of objects, but they're much less fundamentally than EQ or EQL. Okay, I don't understand why this matters. So, okay. So, equal also works on lists that happen to have all of the same elements in the same order and stuff, recursively. And it also works on strings. Wait, does EQL not work on strings then? I'm curious. Oh, okay, EQL does not work on strings, but EQL does work on strings. And then there's also equal p, which is not case sensitive, but is otherwise very similar. And it also will say that floating point numbers are equal to their equal p to their non-floating point counterparts. There's other stuff, but yeah, equal p is kind of the most broadest of them all. So I guess we could use that if we wanted to, but EQL is really the fastest that's practical to use for simple types. Okay, now we go on to formatting Lisp code. Basically, just let Emacs do it. Emacs knows how to format code. For example, if I copy this code here and I paste it into the editor, there we go. I'm not sure what these weird E characters are, but yeah, even if I just even if I just have all of this stuff, I don't know, let's say in a weird position, I can just re-indent it with Emacs, and Emacs will do it correctly. The Lisp reader does not actually care whether or not the code is indented, but they kind of do it for you. And there are rules, though. You just want to try and align it how it looks good. When in doubt, Emacs and Slime know how to do code indentation, so I'm just going to not worry about the rest of this. There's some rules about like special forms versus functions You don't really want to put the closing parentheses trailing, unless you do because you're trying to write something in the middle of function. But it doesn't matter. It's fine. It looks better when you collapse them all onto the end of the line itself. Also, comments have semicolons. 4 semicolons are used for a file header argument. Okay, so I should put 4 there. If you look, there's 4 semicolons there. My editor, the editor theme in combination with the way the terminal transparency is working makes it impossible to actually see those semicolons. But trust me, there are 4 there, and then 3 is like big paragraphs at the top of files, same way as for Emacs Lisp. And then 2 semicolons just like for code that you've commented out. Hello, I'm reading this book on Chapter 8 as well as SICP. Cool. I want to get to that one eventually. I might do something closure related first, though. That sounds cool. Yeah. Yeah, we're on Chapter 4 right now. Just right at the end of it. I'm gonna try and breeze through, though, because a lot of this stuff is kind of self-evident. Or just too confusing to bother with and doesn't matter. It's kind of weird how close those two opposite categories are. So yeah, that's basically all there is to that. So this chapter goes, this is chapter 5, goes into more depth with functions, which is the bulk of the language standard, defines functions. Macros are important, but functions are, you can't really have them without functions, so. The way you define functions is with defun. Boom. Which is short for define function, and it's the fun thing to say. Not sorry. Any symbol can be used as a function name. We already talked about some exceptions to that on the last stream, but literally anything is valid. For example, as an example, if I wanted to say define a function using Japanese characters, I could do that with no problems whatsoever. Right. So now if I type those back in, boom. Functions can have any name whatsoever with any characters in them. These people don't necessarily want to tell you this, but you can absolutely just put non-ASCII characters in your function names. It's totally fine as long as your computer is made after like the year 2000. There are probably reasons not to do it, but I don't like those reasons, so I'm going to pretend they don't exist. So yeah, there's different ways that you, because of how many different characters can actually be put in function names, you can name functions, you can like draw little pictures with the arrows and stuff in them if you want to. Like a dash and then a greater than is an arrow and stuff like that. Compound names, you get to use hyphens, whereas most... Can you name your function defun? Yes, you can, but it will probably break something. So I really don't want to, because I'll have to restart. I'll have to restart the Lisp environment, but you know what, one? That is pretty funny, so I'm gonna do it. Yeah, I want to do it. Format true, trolled thou hast been trolled. By the way, I'm sorry about the, Oh dear. Okay, apparently looks like you can't do that. Lock on package Common Lisp violated when proclaiming defn as a function while in package Common Lisp user. Okay, apparently they really don't want you to be able to name a function defn as a safety measure. Now I'm curious though, if we go to an elisp buffer, can I do that now? Oh my god, I can. So now, if I go defn, it's going to error, but... So basically, I've just broken this this instance of Emacs. And we're going to just pretend that didn't happen. So basically, yes and no. There is definitely a way you could get around the block on that, but you probably don't want to, because defn is so useful for defining functions. It's the old thing of, like, could God make a rock so heavy he couldn't lift it? First of all, no, but second of all, like, why bother? Maybe that's not a perfect analogy. So functions have parameter lists, which are mostly simple. For example, just an empty list means no parameters, but more parameters, there can be more complicated things. You can put a string after the parameter list, like, for example, on the next line. You can name it, but you can't call it. No, it won't let you name it. See, all I did was evaluate that definition, and it's complaining that I'm not allowed to define it, or redefine it, rather. There's definitely a way to get around that, but I don't want to. And I'm glad there's not that. Yeah, documentation strings say hello with style. Cool. So, yeah, the hello world function, or this Ohio that I made, which is basically just the same thing. Defn is what actually puts the function together. The name is Ohio, or in the example it's hello world, but that's boring. And then it's got an empty parameters list. And then we've got a string here, which we could also get rid of if you wanted to. I'm just commenting it out because I didn't feel like deleting it. And then the actual body of the function. Defn verbose sum. Okay, so this example is just a wrapper around plus that also will describe what it's doing. So if we just go up here and run verbose sum, you can see that it takes an x and a y, which are just going to be 2 and 3, and it will format a message about those, and then it will just return the value as well. Summing 2 and 3 plus xy. Boom. Got 'em. That should be pretty self-explanatory. It's basically the same as most other programming languages. You've got your function keyword, you've got the name of the function, and argument list. The one thing that's a little bit unusual about Lisp is that the documentation string is built into the function definition, and it's right there, which is nice when you're editing the environment itself, to not have to just kind of remember what everything does or have really long names. You can just have a short name for a function and know what it does from the documentation string, and that's pretty nice. the next part of this goes over parameter lists. There are simple parameters, for example, the x and y we did for this function here, which are just bound to the subsequent elements of the list where you call the function. But there are also more complicated ones that you can put, such as optional ones or key arguments and stuff like that. So the simple way of doing it, optional arguments is pretty simple, and it's the same as an Emacs. You can just put an optional. So if I do defin foo AB, an optional C and D, and then the body of the function will consist of listing A, B, C, and D. Now, if I foo 1 and 2, that's fine, and C and D are just bound to nil. If we just do foo 1, it will error because 1 and 2 are not optional, so they're required. A and B are not optional, so they're required. We can also, of course, just keep adding. So now only C. So C is optional. So each of them, basically, after the optional symbol, are individually optional, but they're just going to get assigned an order. See, now with 4 arguments, all of those are defined. What happens if I put a 5th argument here? I'm actually kind of curious. That has an error because invalid number of arguments 5. Right, because only 4 arguments were defined, it doesn't know what to do with the 5th one. So that's simple enough. Just n optional means all of the extra arguments, you don't actually have to call them, and if you don't, they'll just be nil. Pretty straightforward. Of course, you might want a default value other than nil, which is why it's optional, why it's also possible to define a default value, which you do by putting them in a little pair like this. So, okay, that's fine. So if we were to just foo with 2 arguments, the first 2 get returned back. C is not specified, so it's nil, but we put D having a default value of 10. So that's what got returned. I do not think that eLisp has that, at least not natively, but Common Lisp does. It's pretty self-explanatory, I think. Not too big a deal. However, there are perhaps other ways of... Hang on. Okay, I see what they're trying to say. So you can also put 2 in there at the same time. Wait, okay, hang on. I'm misunderstanding something. Optional. So, okay. So you can tell it to just give the value be the same as the other one. Oh, I forgot to remove that. Okay, this will work now. So the argument C gets bound to A because they're evaluated sequentially, I guess. That's a little bit more confusing, but I think it's probably fine. But it is also useful to know whether the argument was actually specified, because, like, the same thing would happen if we did foo121. See that? But those were specified differently. The solution is to put another variable in this pair, so it's now a triple, which is a supplied p, and that's just a convention. You could put anything for it. Supplied p, and now foo12 would return the 121 and then nil because c was not supplied, whereas foo121 would return 121t because that third argument was explicitly, given, not just inferred from the other arguments. So that's pretty easy to understand, I think. We have not gotten to the confusing part yet. Okay, next we have the and rest parameters. Some functions take an arbitrary number of parameters and they can just kind of deal with that. For example, format does that. Plus can do that. You can just plus, and you can keep plussing whatever you want, and it'll just plus them all together. Like, it's no big deal that you put more than 2. You can even have just one argument to plus. Can you have 0 arguments to plus? I'm curious. You can, and it just returns 0. That's great. I love that. Nice little Easter egg. Oh, it actually says that in the book. Whoops. Should have read the book, but I'm not going to. So you can do kind of parameters manually like that with however many by just putting a lot of optionals. And also plus would have to have an infinite number because it can take an arbitrary number of parameters. So the easier way to do this is with a different keyword called and rest. So we could define a function bar that takes and rest args and just returns its args back. So now if we wanted to bar with no arguments, it would return nil because that's what the there's no parameters. If we want to bar 1, it returns a list of 1. And this is interesting because the way that and rest works is it just binds the entire args variable there to the complete list of arguments, just whatever is there. So if we keep passing it more and more, it gives us all of them in a list. And again, the reason that it returned nil with nothing was because the empty list is nil. So that is probably how functions like format and plus work internally. Or not, who knows, doesn't matter, they work. Next we have keyword parameters. Keyword parameters we've already seen a bit of with our association lists earlier. And they're basically the same as named parameters. Or like if you were in Bash or something and it just had like dash arguments, it's the same idea. So the way we do this is I'm going to deviate from the example a bit because I want to just kind of keep everything here. So the way we do that is with and key, ABC, for example. And then we can just, for simplicity's sake, return the list of all of those. So Baz with nothing returns a list of 3 nils because none of the arguments were defined, but we can actually give keyword values to them. For example, here setting A to 1 and B to 2. But we could also set A twice, and it would just get, it would keep the first one, I guess. But we can also set them out of order, so like putting B to 1 and A to 2, still A is 2 and B is 1, even though we've reversed the way in which they're shown there. And keyword parameters are really nice for being verbose and specific about what exactly you're doing. It's good for like user-facing functions, but it does start to get a bit long-winded. If a given keyword doesn't appear in the argument list, its parameter is assigned its default value, which is nil unless you otherwise specify it, which you can also do with the with putting it in a list, like for example, like that. So now B is 1, A is 2, and C is 10 because that's the default value we have assigned for C. And you can also do that with supplied P type parameters, as we showed earlier with foo, with the optional arguments to test whether or not it was explicitly given or just assigned a default value. And you can actually... Okay, also if for some reason you want the keyword the caller uses to specify the parameter to be different from the name of the actual parameter, you can replace the parameter name with another list containing the keyword to use when calling the function and the name to be used for the parameter. So for example, we could do a list with colon, something like that. So now A is no longer defined keyword, so we have to do something like colon apple, I guess. But the actual, internally, it's still called A, it's just a layer on top showing it as apple. So that's a thing for some reason. I like how it says, also, if for some reason, like, why would you want to do that? And I agree, why would you want to do that? The style is mostly useful if you want to completely decouple the public API of the function from its internal details, usually because you want to use short variable names internally but descriptive keywords in the API. Okay, I could see that. I could see that. Every now and then, maybe. But also, I'd never do it because it's too confusing to bother with. Mixing different parameter types. You can mix parameter types. It's possible, but rare to use all 4 flavors of parameters in a single function. Whenever more than one flavor of parameter used, they must be declared in the order we discussed them. So first, just simple required parameters, and then optionals, and then rests, and then keyword parameters. Okay. And it kind of gets wonky, some ways of combining them. Okay. So basically we should just try to not bother, but know that there are ways of applying different parameter types to functions. In general, if you find yourself writing a function that uses both an optional and the and key, you should probably just change it to use all of the and keys. They're more flexible, and you can always add new keyword parameters without disturbing any existing uses. And also, you can remove them too if you want. And that's about it for that. I'm not going to go into the weeds with parameters any longer. Function return values. Function, when called, returns a value. And the value it returns is the last expression that gets evaluated. However, sometimes it's convenient to be able to return from the middle of the function, such as when you want to break out of nested control constructs. In such cases, you can use the return from special operator to immediately return any value from the function. And return from works a little bit differently from how it looks like it does, but it's actually fine. So this is essentially a lot like break statements in other languages. And I'm just going to copy this function in because I'm tired of thinking right now. But the thing is that we also have... Okay, there we go. So now if we want to... What this function does is it finds the first pair of numbers less than 10 whose product... So multiplying them is bigger than plussing them. And it uses return from to not have to loop through everything after it finds those. So for 1 it's 1 and 2, for 5 it's 1 and 6. Right. For 12 it's 2 times 7 is... Okay, I kind of see what it's doing almost, maybe a little bit. Basically, but the only reason it's so quick is because instead of just working up through all of the numbers forever, it quits immediately once the condition is reached with its return from statement. Admittedly, having to specify the name of the function you're returning from is a bit of a pain. For one thing, if you change the function's name, you'll need to change the name used in return from as well. But it's also the case that explicit return froms are used much less frequently in Lisp than return statements in C-like languages, because all Lisp expressions evaluate to a value, so don't worry about it, basically. But return from does exist. Cool. Functions as data, aka higher order functions. This was one of the original advantages the Lisp had over other languages that existed way back in the day, is that since code is data and data is code, functions are not like particularly special or unique or fixed. So when you defun something coming from C++, the way values are returned from function Lisp surprised me. Yeah, I can't really speak for that. I don't really have much C++ experience, but it is kind of refreshing. Here's an even simpler example. Okay, we could, like, I don't know, defun, and then we could return. We could just put a bunch of things that all evaluate to themselves in the argument. Oh, and I need to put actual argument lists there. But basically, the function will evaluate all of those things, but then it will only return the last one. So that's pretty nice. In Lisp, functions are just another kind of object. When you define a function with defun, you're creating a new function object, and you're giving it a name. There's also lambdas, which are what are called anonymous functions. So it's just a function object that exists without really a name. And there's implementation details with that, but it doesn't really matter. It's common in functional languages. Okay. Yeah, Lisp is somewhat arguably a functional language. The problem with that, though, is that everyone, means something different when they say functional language. When Lisp was invented, it was functional because it had functions, and it had... functions in Lisp are more than just named blocks. We can introspect... I don't know what introspection is, but... it will... function is an actual, type of object. Whereas in other languages that existed, like Algol and BASIC, a function is just a set of lines that you can, pretend to splice in at different points in the program. It was much more lexical sort of a thing than, proper control flow as such. Okay. But yeah, since functions are objects, we can refer to them. This function command, I guess, takes the name of a function that will return the actual function object inside of it, and hash quote is the shorthand for that. There's really not a ton you can do with them, though, but there is. But yeah, no, because functional languages, you can talk about Lisp compared to C is functional, but compared to Haskell, no possible way. Because functional has to do with mathematical purity or something. I don't even know quite what the deal is with Haskell, with functional programming as it exists now. But it's definitely not the same thing as it was back when Lisp was considered a functional language. Because Lisp has tons of side effects, it has tons of indeterminate results. It is not deterministic, I guess. Might be the way that works, but I'm not completely sure. That's not what the stream is about. Right. Calling functions. Now, since functions are objects, you can actually use this other function, or this construct funcall, hash quote, and then the name of the function. And it will do the same thing as if you just run the function in its list. Functional languages are the ones that use functions as input to others so you can compose them. OOP is the same but with objects. Objects take another objects. Okay, but then wouldn't a function... Wait, so in OOP, is a function an object? Or... I know there's methods too in OOP. Are those the same or different from functions? Because I've only used one object-oriented language, which is PowerShell, which is just kind of it's C# with Perl smacked on top of it. So, but in PowerShell, you can define functions just like this with defun, and they're just kind of commands that you can run. But then there's also methods that get called from classes, which have a worse syntax. Purity is another thing that Haskell has made almost required. Yeah, it definitely seems like the discourse is changed just by the existence of Haskell, doesn't it? So, if we already know what function we're going to be calling, putting funcall everywhere isn't really practical. It doesn't really matter, and the compiler is already doing it for you, basically. However, what What makes funcall cool is that you can use it with variables. So if I want to set q, wait, I forgot how parentheses work in this language. I can't believe myself. So now, this variable 5fn happens to be function 5 is what it's bound to. So now if we wanted to funcall this variable, the variable gets evaluated because funcall is just a function, and then it returns the value itself. C++ methods have an implicit this pointer to the current instance of the object. Okay. But then, okay. One thing at a time. I'm like really confused now. Please bear with me. Thanks. How many people are? Okay. It says 1, but I know there's 2. 1, your internet sucks. I hope you know that. So they give this example of a more complex function which can take lots of different, basically it uses a funcall in order to call different functions in the same way programmatically, and that is the main reason to use funcall. It's just kind of a neat way of saying, hey, I don't necessarily know what this function is, but I still want to call it anyway. And I don't know if we actually have mentioned this specifically yet, but variables and function names are different in Common Lisp, which is the same way as they are in Emacs Lisp. This distinction is sometimes called Lisp 1 versus Lisp 2, like 1 versus 2 namespaces, but that's not completely accurate. Can you funcall a number? Let me try it. I don't think so, because the function value 5 is not a function or a symbol. That is the error I am getting when trying to funcall a number. I'm sure if we wanted to define just the number 5 as no values and just return 5. Oh, that doesn't work because you're not allowed to assign numbers function names. That's basically the problem with that, I guess. I'm a little bit surprised that you can't. But yeah, if we want to use this plot function, they're suggesting wait, what? I'll call 5 hyphen what? Oh. Okay, something broke, and I'm not sure what it is. But it's fine, because everything is still fine. Okay, wait, can we... Okay. Okay, my Emacs is completely broken now. I don't know what happened. So what I'm gonna do is I'm just going to open a new terminal And we're gonna deal with this. Look what you made me do. 1. Okay. Does that work? We're going to recover this file. Listing directory failed, but access file worked. Okay. You know what? All that stuff was stupid anyway. We can just copy it back. So copy this. Okay. And go down here. And go down here. And paste it. And get rid of these weird broken characters. Maximum destruction. Yes. Wait, okay. And the problem here is that I didn't actually set up slime editing mode. So if we do that, boom. It needs arguments, so if we just call it with I don't know, whatever numbers, it will plot out a graph in ASCII text of whatever that looks like. And the function that they're using for the example is exp, which is the exponent. And that's basically, it's fun calling. It has different outputs depending on what function we pass to it, because it is calling that function within the actual body of the function itself. And that's why funcall is pretty good useful. Funcall, however, doesn't do you any good when the argument list is known only at runtime. For instance, wait, what? Okay, so what they're talking about is okay. I'm not quite sure what the direction they're coming at this from is, but besides funcall, there's also apply. And apply is similar, except instead of taking just wait. Hang on. Apply can take okay. Apply basically lets you use a list as a list of arguments instead of putting them all within just the funcall calling itself. And there's other yeah, okay. Basically that's apply. It's like funcall, but maybe more overpowered, but hard to remember how to use. I barely even care anymore. I've been streaming for an hour already. Cheese balls. So, functions are nice and all, but sometimes you just want to make a function and only use it once. And you don't really need to have it be everywhere. A lesser language, you would just have to make a function with an obscure name and then only call it once. But in Emacs, in Lisp, and this is true for all Lisps, and even coming to be for more languages more recently, you've got these things called lambdas. And a lambda is an anonymous function. Anonymous means that it doesn't have a name, like posters on certain message boards don't get assigned, don't have accounts, don't really sign in, they just kind of post wherever, and the system just describes them as anonymous or anon. So lambda here works similarly to defun, except it does not have a name. It just takes an argument list and a body. So, for example, this very simple lambda here that takes nothing and returns nil, the return value of that down there, which I can't really show with my mouse because it disappears when I move my mouse, but if you can see down on the other side of the screen there, it's returning a function object that just consists of a lambda and numbers that the compiler uses to refer to it, which is separate from how, because before these old functions we had, it was actually, they're gone now, that's right, we restarted. But yeah, so lambdas are somewhat neat like that. They create a function, and of course you can also just call this function, and when we call that line, which is just a list containing the lambda with no arguments, it just evaluates the lambda. If we were to give the lambda more arguments, and then we would have to call those arguments, it can still display them as you do. But the first element of the list is just this lambda expression, which is getting converted to an anonymous function. It's used in that one place and that place only. It's remembered just long enough to execute it and no more. I mean, like, realistically, it's there in the air for a while until the garbage collector gets rid of it, but it doesn't matter. Of course, you can also use this. Excuse me a second. Well, there goes all my viewership. Dog started barking because we were getting a package. I don't know what's in it. This is my dad's house. I'm watching it for the week. And he must have ordered something. Give me a second, just breathe. Lambdas. Lambdas are kinda nifty. You can also use funcall on a lambda expression, and we can also set variables to lambda expressions. So now, it's going to error about that variable not being defined because setQ was complaining. But yeah. So now if we look at the value of myFun, just by evaluating the variable, it returns this function object, which consists of a lambda taking a certain number of arguments that it knows. So we can, of course, phone call with the variable, which will again get converted into a defn with the right number of arguments. Or we could apply it if we want to give the wrong number of arguments. Very fun. That is the basic utility of lambdas. They're functions that don't really have a name in the function namespace, and you can kind of pass them around however you want. So that means if we want to apply this old plot function, we don't have to define a function just to be able to plot it. We can actually simply, oh right, yeah. Times 2x. I'm just copying what's in the book here. So you can see it returns that same kind of stair-step pattern. Lambdas are that's the main utility of lambdas. They can be used where a function would be overkill. Okay, here's an actual footnote about the whole functional thing. Despite the importance of functions in Common Lisp, it isn't really accurate to describe it as a functional language. It's true some of Common Lisp's features, such as its list manipulating functions, are designed to be used in a body form style, and that Lisp it has a prominent place in the history of functional programming. McCarthy, the inventor of Lisp, introduced many ideas that are now considered important in functional programming, but Common Lisp was intentionally designed to support many different styles and paradigms of programming. In the Lisp family, Scheme is the nearest thing to a pure functional language, and even it has several features that disqualify it from absolute purity compared to languages such as Haskell and ML. There's a whole bunch more footnotes, but we're not going to go over them either. Alright, now that we've gone over functions, it's time to do Chapter 6, variables. If you want, I could also not. I don't know. Yeah. Let's just breeze through this. It shouldn't be too long. There's some complicated stuff, but I mean, variables are simple. They're just variables, right? How complicated can it get? Okay. Common Lisp supports two kinds of variables, lexical and dynamic, which are similar to local and global, respectively. So a dynamic variable is like a global variable. It just is what it is everywhere in the environment. Whereas a local variable is only defined within a specific block of code. We saw an example earlier with let, which binds things locally, lexically. The book takes care to note that lots of languages that claim to have local variables they're just global variables that are being hidden elsewhere. But Lisp lexical variables are truly lexical, like they only exist within that space. I will get into how that works in a bit, I believe. So basically, all programming languages that have variables, variables are just names for places that hold a value. But types are a little bit, yeah. So Common Lisp is dynamically typed. Most Lisps are mainly dynamically typed. There are ways of specifying types if you want, but this is dynamically typed. I know that Immortality in chat, or sorry, one said dynamic typing is stupid. Why did you say that? So the whole dynamically typed versus statically typed one debate, I guess, is... Let's see, what are my thoughts on that? Well, so it's like... It's going to matter what the type of something is, but it's easier to not have to say it. I guess that's where I am with that. If you do have to, something may have gone wrong. Or, I mean, if you're getting type errors, something has gone wrong, but like, basically every error is in some ways a type error. And all you're doing by being super explicit about types, being static about types, is you're, I guess you're catching the errors a little bit earlier, which might be a good thing, but it's harder to program with, because what if you just suddenly decide, oh, I want this to be able to take multiple types of things? And there's ways around that, of course, by just using a vaguer type, but I don't know. Yeah. So now we get into... So, okay, hang on. All values in Common Lisp are, conceptually at least, references to objects. Consequently, assigning a variable a new value changes what object the variable refers to, but has no effect on the previously referenced object. It's not actually getting clobbered, it's just not being looked at anymore. However, if a variable holds a reference to a mutable object, you can use that reference to modify the object, and the modification will be visible to any code that has a reference to the same object. This gets into, and I don't know if they're going to specify it super heavily here, but pointers. Sometimes people argue about pointers, about whether you should be assigning things specific places in memory or be assigning... Like, this is the whole thing with C. It's like, oh, if you understand pointers, you understand everything. It all makes sense. Well, the way that Lisp works is every variable is a pointer, basically. Or every variable that you assign is getting assigned to a pointer that goes to a different value. And that's just what a reference is. So, it is using pointers under the hood, but you basically never have to actually manipulate them. That's just part of the language standard does it for you. Because we're working on a totally different level with Lisp. There are different ways to make new variables. Most obvious one, as we saw with all these functions, is you put arguments for the functions, parameters, and the parameters will be bound within that function. Each time a function is called, Lisp creates new bindings to hold the arguments passed by the function's caller. Binding is the runtime manifestation of a variable. Okay, so it's just what it's set to within that scope. A variable can have many different bindings during the run of a program, or even at the same time. For example, if you're running a recursive function, each like recursive step of that is going to have a different scope of variables that are rebound. As with all Common Lisp variables, function parameters hold object references, pointers, so you can assign a new variable. I need to be reading less. I need to be moving faster. This stuff is getting overcomplicated unnecessarily by me. Yeah. So, like, if you happen to run the same function twice at the same time, those scopes are still distinct even though it's the same function being run. It creates an actual separate environment for it. But of course, variables that are like pointing to something else that's outside of that environment will be accessing the same thing in parallel indirectly through the variable binding. Now, there's also let, and let is pretty fun. If you're familiar with Emacs Lisp, it is the same exact idea. It literally just the exact same. Actually, I'm slightly curious now. How does CL let? Oh, CL let F? Yeah, okay. No, that's the same. Okay. Basically, yeah, it's literally just the same. Let is, it takes a table of variables with their bindings and then has a body in which those variables are bound to those things. And until you work out what is, or are told what let is doing, you don't quite understand it. But once you do, it's pretty simple. The syntax, I've seen people complain about it, but it's really not that bad. Yeah. And as with function parameters, the values within a let binding they're lexically bound. They only exist within that let block. So here's kind of a visual example of there we go. No, yes, okay. Here's a visual example of what that looks like. So we've got a function definition with one argument that's x, and in the beginning we just have a format expression that does not change the value of x, so x is bound to the argument of the function. But then we have a let binding that rebinds x to 2, so within that whole block x will be 2, except there's another let binding inside of that will bind it to 3 instead, so that x is 3. But if you go back outside of that block, x will still be 2 again, and if you go outside it will be whatever the argument to the function was. Each reference to x will refer to the binding with the smallest enclosing scope. Once control leaves the scope of one binding form, the binding from the immediately enclosing scope is unshadowed, and x refers to it instead. And there's a little table of what that looks like for the different values that the variable has within the function. It's easy to observe but hard to explain, so I'm not going to. There are other forms that do this besides functions and let bindings, but everything is kind of the same in that regard. It's the same sort of idea of a lexical scoped binding. Nobody's watching my stream right now. I feel like I need to get to the end of this chapter, though. What chapter is this? This is chapter 6. In chapter 7, we're going to meet do times, which loops over a variable, but in the same way as let, but multiple times, of course. There is also let star. Let star is the same as let, except the variables, if you have multiple variables within a let star binding, they get evaluated sequentially. So let's see what happens if we try to let x be 10 and let x be 10 and let y be, okay, I have to go have a nice learning session. Thanks, see you later. I may or may not end the stream very soon. Probably will, honestly, but we'll see. I do want to get to fun stuff next time, if not. Yeah. Okay. You know what? You know what? Screw it. I know how let works. I don't need to explain it if nobody's going to be watching anyway. Lexil variables and closures. Closures are the weird stuff, and I think we need... closures are getting into like what I mentioned with let over lambda. They do a lot of closures in that book. And it's a little bit crazy. Basically, you can like change the values inside of let forms that you've abandoned. You can like move back into them later, and so you can just have these objects. Well, there's a whole bunch of stuff with like the ontological relation between closures and objects, which is pretty neat. But yeah. I am excited for that, but not excited about it right now, so I think we're just going to call it a day. Thank you so much for watching, if anybody's still here, which they're not. I have been MitchMark42, and I shall see thee in the next one. Bye.